So what we are going to be learning today is how to calculate half-life. Half-life is very important in many different areas of life, but every isotope that you find of an element has a half-life. There's an amount of time that it will take for half of that isotope to decay. Don't forget an isotope like iodine-131 or technetium-99. Those isotopes are different types of that element, or I'm sorry, not different types. They're the same element with a different mass. So they have a changed or a different number of neutrons. Same number of protons though. All iodine has the same number of protons, but this change in the mass just means it's an isotope of that element. But we're going to calculate half-life. That's important to know. It's important to know how long it takes for something to decay, because it may tell you what mass you started with, or if you know the half-life and you know your starting mass and your ending mass, it can tell you how long it will take for a certain amount to decay. So let's just look at an example here. We always set half-life problems up the same way. When we're going to work out a half-life problem, we have a T-chart. Our time goes on the left and our mass goes on the right. We always start at time 0 because when you are adding a half-life, that'll be a certain number of time, and you want to add that to your starting time of 0 so that we always start at the same point, time 0. Iodine-131 is used to destroy thyroid tissue in the treatment of an overactive thyroid. The half-life is 8 days. If a hospital receives a shipment of 200 grams, that's our starting mass, how much iodine-131 would remain after 32 days? So we know a couple things. We know our half-life, we know how much time we have, and we know our starting mass. So we want to know what mass will be left. And you always know the starting and ending on one side. Here we know our half-life and our ending time. Now for the half-life, what we need to do is we need to count by our half-life to get to our ending time. So if our half-life is 8 days, every 8 days, half of our sample is being released. So our half-life is 8 days, we're going to go to 32 days. So my first half-life is 8 days. My next half-life would be 8 more days. 8 plus 8 is 16. My next half-life would be 8 more days, which would be 24. My next half-life would be 8 more days, which would put us at 32. Okay, so I'm counting by my half-life to get to where I need to go. So 0, 8, 16, 24, 32. I'm adding my half-life every time. So on this side, we add the half-life. On this side, we take our starting mass, which is 200 grams, and it is very important that you line them up. And we are going to divide by 2 because we are doing, every time there is a half-life, half of our sample decays. So after one half-life, 8 days, we have 100 grams left. After 2 half-lives, 16 days, we have 50 grams left. See, I'm dividing by 2. Then we divide by 2 again. After another half-life, we have 25 grams. And after another half-life, we have 12.5 grams left. So it says how much would remain after 32 days? At 32 days, we have 12.5 grams remaining. Okay, so that is how we would work out the first question. The second question is very similar. It just says technetium-99 is used for brain scans. A lab shipment receives 200 grams. That's our starting mass. How much will remain after 24 hours if the half-life is 6 hours? So on this side, where we divide by 2. I think most of you know that halving something is dividing it by 2. But we're going to draw our T-chart right here. Time is going to be on the left. We always start at time 0. Mass will be on the right. Our starting mass is 200 grams. We want to know what our ending mass will be after 24 hours. Well, how do we do that? Our half-life is 6 hours. We're going to add our half-life because we know that after every 6 hours, half of it decays. Another 6 hours would put us at 12 hours, be 50. Another 6 hours would put us at 18. That would be 25. And another 6 hours would put us at 24, and that would put us at 12.5 grams being left. 12.5 grams is how much we have left after 24 hours because we add our half-life on this side until we get to the ending time, and we divide by 2 over here. Okay, so let's look at a different example. Mercury 197 is used for kidney scans. Has a half-life of 3 days. We have 32 grams of mercury ordered, but it takes 15 days to arrive. So here they give us our starting time and our ending time and our starting mass. We want to know how much is going to make it after it takes 15 days to get there. So we have our starting time, 0. Our starting mass is 32 grams. All right, we know that our half-life is 3 days, and we're just going to take 15 days to arrive. So we're going to count by our half-life, 3, 6, 9, 12, 15. And on the right-hand side, we are going to divide by 2. So we're halving our mass. Every half-life, half of our sample is left. 32 divided by 2 is 16 grams. It's really important that you line it up perfectly so you don't miss out and divide too many times or not enough. 16 divided by 2 is 8 grams. 8 divided by 2 is 4 grams. 4 divided by 2 is 2 grams. And 2 divided by 2 is 1 gram. So 1 gram of that 32 gram sample will arrive in that shipment because so much is decaying every 3 days. All right, the half-life of strontium-90 is 25 years. How much will remain after 100 years if the initial amount is 4 grams? All right, so we start at time, 0, and our starting mass is 4 grams. So our half-life is 25 years. We want to go to 100, so we're going to count by 25. 25 plus 25 is 50. 50 plus 25 is 75. 75 plus 25 is 100. Just be sure you don't think you're multiplying here. We are just adding our half-life every time. Or if it's easier to remember, just say count by that number. So here on the right-hand side, we divide by 2. 4 divided by 2 is 2. 2 divided by 2 is 1. 1 divided by 2 is 0.5. And 0.5 divided by 2 is 0.25. All right, so our mass that we will have remaining after 25 years is 0.25 grams. All right, last example. If the half-life of uranium is 70 years, that means we're going to start at time 0 and count by 70. But we don't know the ending time. So this is a little bit different. This is how many half-lives will it take for 10 grams, that's my initial mass, to be reduced to 1.5. So now you know that we're going to end with 1.25 grams down here. So all I know is that my half-life is 70 years. So what I need to do is I need to figure out what the question is asking. It wants to know how many half-lives. So how many times do I have to add my half-life to get down here to 1.25 grams? Well, here I've got to go ahead and divide by 2. 10 divided by 2 is 5. 5 divided by 2 is 2.5. And 2.5 divided by 2 is 1.25. So our half-life is 70 years. That means we add 70 to 0 and get 70. 70 plus 70 is 140, and 140 plus 70 is 210. So what it looks like the answer would be is yes, it takes 210 years to get to 1.25 grams. But the question says how many half-lives? So how many times did we add our half-life? We added it 1, we added it 2, and we added it 3 times. So it took 3 half-lives. So what's important is to look at the problem and see what it is asking before you start working it out. Now I want to show you how we find half-life on a graph. So here was our first problem about iodine 131. So the big concept here is every time we add a half-life, which is a certain amount of time, half of our sample decays. You know this because things have expiration dates. They know what the expiration date is because we know how long it takes for something to decay. Okay, so right here, this is iodine 131. So if I was to title this iodine 131. This is my percent of sample. So I have 100% of my sample. At time 0, I got everything. I got 200 grams. Okay, so I have 100% of my sample at time 0. After one half-life, which is 8 days, I have 50% of my sample, half of it. Okay, after 2 half-lives, which is 16 days, if you're looking at it out of 200, 50 is 25%. So after 2 half-lives, I have a little bit less of my sample. After 3 half-lives, I have 12.5%. And after 4 half-lives, I have even less. So what you're going to notice is a half-life graph will normally look sort of like this. And what I want you to see is when we're finding half-life from this graph, the goal here is to find out what is the half-life of this sample. Well, I know that half of our sample, so our percent of the sample, half will be left after 1 half-life. So if I start at 100%, half of that will be gone after 1 half-life. So my half-life is 8 days. After 2 half-lives, I do half of 50, I come down to 25. That's another half of the sample. So just remember, we started our total, divide by 2, so cut it in half, down to 50, and come over, and that tells us what our half-life is. It's 8 days.